All right, so with organic chemistry, we have started off by noting that organic chemistry of compounds that are carbon-based, okay? So we looked at the electronic structure of carbon, right? And we saw that carbon has got a valency of 4. So not a valency of 4. It's got a valency of 4, and it's got 4 valence electrons. However, when carbon is on its own, it only has 2 half-full p orbitals. So when it bonds, something else needs to happen. So when it bonds, it undergoes something called sp3 hybridization, right? So what happens then, we see, for instance, in the case of methane, that the 4 valence electrons are actually in half-full orbitals, so that you have 4 spaces for electrons to be shared from other atoms. Right, we spoke about the fact that the Cooper notation can also be called the structural formula. We are going to refer to it now in organic chemistry as structural formula, not Cooper notation, okay? Lewis diagrams is the dot and cross method, okay? We are not going to continue to represent organic molecules with dots and crosses, okay? We'll start off when I introduce a new type of compound, I will show you what the dot and cross looks like, but we are going to use structural formulae. We are going to I've introduced the idea of condensed structural formula, which yesterday didn't look any different to a molecular formula because we were dealing purely with methane. Right, so there we spoke about the hybridization. The hybridization leads to what we call a tetrahedral structure. We looked at alkanes. So an alkane is a family of organic compounds consisting of only carbon and hydrogen atoms, and carbon-carbon bonds and carbon-hydrogen bonds, okay? And, you know, you look at this and you go like, okay, boring. Humans fight wars over this stuff. We call it oil, okay? Oils are hydrocarbons, okay? Our octane and our hexane and our propane and our butane and all of that, ladies and gentlemen, those are fossil fuels, okay? Living in this area, we know there's a massive refinery up the road. Okay, what does that refinery do? Declan?
It splits up oil into different compounds.
Yep, it takes crude oil, which they call the black gold, and it splits it up by means of fractional distillation. Those massive columns basically splits it up into propane, butane, hexane, octane, and we get all sorts of things, jet fuels, kerosene, as the Americans call it kerosene, we call it paraffin, and. Okay, now, but they are, for the most part, they're hydrocarbons. Okay, so our world's economy is based on what, to a large extent, on what we're talking about now, alkanes, okay, hydrocarbons. Oh, our use of it is also damaging the environment. Just a thought. Okay, cool. So then we learned about naming the prefixes: meth, eth, prop, but, pent, hex, hept, oct, non, dec. Okay, so the carbon backbones, we are going to use the prefix to denote how many carbons are in the backbone. When it comes to alkanes are what we call an homologous series. I will still define that. Homologous series is a family of compounds that have got the same structure. So they have commonalities. We classify them according to the type of bonds that exist in the carbon chain, and you will see later on also functional groups. So methane, ethane, all right, I see some of you have been drawing it like this, where you've got the zigzagged carbon backbone. There's nothing wrong with that. But you don't need to do that. Okay? So if we now, and I just want to quickly talk about different ways of representing this, and the reason being is I saw one or two of you do this. I saw one or two of you representing your molecules like this. All right. Now, is this wrong? Trent, do you think this is wrong? Okay. It's right and it's wrong. Okay. At university level, that is fine. It's acceptable. It's okay. We know there's hydrogens there. On school level, NSC, it's going to be marked wrong. You have to put the hydrogens in. As a matter of fact, at university, they go one step further. They represent each of the carbons with a node, like that. So that would be how they represent that. So each of these points would represent a carbon.
And they wouldn't show the bonds on the outside.
They don't show the bonds on the outside of the carbon. So it's an even further abbreviation. Okay. Now the reason for that is obviously at university level, we deal with super complex molecules. Okay. And so you'll see as we go along, I will show you that as well to prepare you for university. Okay. Cool. So the homework was to draw the structural diagrams up to and including decane. I'm not going to draw all of them because I want to move on to alkenes and alkynes today. Okay. So let me do one. Let me do, Carl, what would you like me to do? Octane. Okay, so I'm going to do octane. Okay, so let's look at octane. Octane is not a bad one, right? We use it for petrol. Okay, so here goes. Octane. We've got, I just want to use the same color for the prefixes. Okay, so I'm going to use red. It's octane. So the ANE tells us it's an alkane. So there are only single bonds between the carbons. Okay. So there's going to be, and the oct tells us that there are going to be 8 carbons. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8. So that is the carbon backbone, octane. Now remember I said to you each carbon has a valency of 4, so they will have 4 bonds. So I'm going to make sure that each carbon has got 4 bonds. Right, and now we need to fill up with H's. I know it's a little bit tedious, but that's what's expected. So there, that is octane. Right. Could I break the linearity of the chain? Well, I certainly can, right? Because if I show you here using my model, and it's important to note this, especially later on, right? If I now have, let's say I have a molecule that looks like this. Okay. What would this be? What would this be?
Pentane.
Meth, eth, prop, but, pent. Hey, it's 1, 2, 3, 4, 5. We don't see any double bonds, so that would be pent for 5 carbons, pentane. I want to show you something. Can you see that these bonds can swivel? Can you see these bonds can swivel? All right? Can you see, because the single bonds are rotational, you can actually rotate them. And that's exactly what happens. They continually are rotating. So a molecule like this will have what we call translational kinetic energy. It'll have vibrational energy, but it'll also have rotational kinetic energy in it. Yes.
So would that make it like more liquidy? Yes.
The liquidity of it is determined by when I take look at the molecules around it, what is the strength of the intermolecular force between it? The structure does determine how strong the forces are. That is the next section we do in organic chemistry, which is called properties of organic compounds. It's to do with intermolecular forces. So you get different types of intermolecular forces. You get, for instance, hydrogen bonding. You get London type van der Waals interactions. You get dipole-dipole, ion dipole. You get the London types is also called dispersion forces, which are very weak. But that's a whole section on its own. We're not going to do that yet. Yes.
What happens beyond decade if you keep adding hydrocarbons?
They just get longer and longer and longer and longer.
There's
no limit. So polymerization, the plastic molecules can be millions of molecules. So there's no limit as to how. Okay, and that's really good because what that means is, and that's linked to something called catenation. So carbon atoms can catenate, they can continue to bond to each other, and that process is known as polymerization. We need to move on, but yes. Did you want to ask a question?
No, I'll just ask
Okay, cool.
is that what Teflon is? Isn't that like a really long?
Yes, so your Teflon is what's called polytetrafluoroethane, PTFE. So what it is we'll see, we're going to get to ethane now. So when you take a whole lot of ethane molecules, but instead of hydrogens in them, you've got fluorines in them. So what you have is tetrafluoroethane as your monomer, and then your monomer is the fundamental unit that gets added, and that forms PTFE, Teflon. Okay, cool. That's polymerization. Okay, so now what I want us to do is I would like us to, and maybe before I go further, I just want to show you how we would represent this using the ultra efficient method. We would say carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, carbon 8. So on university level, if you look at university textbooks, you will see they would represent this like that. They don't put in these bonds, they just give you the backbone. And a little later on, you'll start to see where they might have, a fluorine there, or they might have a chlorine there, that sort of thing. We'll get to that. Okay. Now, all right, so let's look at the next homologous series. We are going to look now at alkenes. Alkenes. So it is a family of hydrocarbons which have C double bond C in their backbones, their carbon backbones. I'm going to say explicitly, this is not the formal definition in NSC. I will still give you the formal definitions straight out of the grade 12 examination study guidelines. If you follow that, you can never go wrong. Yes.
What is that double bond called?
Double bond. Carbon double bond.
Isn't there a name for it?
Double bond.
Single bond is double bond and triple bond.
That's what we call them.
Okay.
Okay. All right. Okay. So that's what we call it. Okay. When we start to get to, for instance, C double bond O, then we call it the carbonyl group. But C double bond C is just a double bond between two carbons. Okay. If we get to carboxylic, what we call the Cu group, C double bond OH, that's got, we'll talk about the functional groups later on. That has got a name called the carboxyl functional group. Okay. Now, let's talk about alkenes. Okay. Do we get something like methane or methane?
Yeah.
Okay, think about this. Okay. Can we get methane? Why not, Mbali?
Because there's a bond between two carbons.
You need at least two carbons. So what's your first compound going to be, Emily Jane? Wow. Oh, my word. I'm sorry, I got that one wrong. I'm having a bad day. What is the first? My mind is like Swiss cheese. What is the first compound in the alkenes? Ethene or ethene. Okay, so let's draw that. Okay, yeah, old age is a terrible thing. Eh? So let's take a look. We've got ethene. All right. Okay, and eth is two carbons with a double bond. Now, what do we? I'm mixing you up with Emily Jane in grade 11. I do apologize. I'm so sorry. right, now, how do we draw this? Yes, Josh.
Would it just be 2 hydrogens for each carbon?
Okay, so remember the circle text. 1, 2, 3, 4. So we are going to need 4 bonds around each carbon. Okay, 1, 2, 3, 4. 1, 2, 3, 4. All right. Okay. Why do you think I draw them at an angle? Because of the repulsion. Okay. If I were to draw it like this, would it be wrong? No, it wouldn't. But generally speaking, we know that these lines represent 2 electrons. So they are negative. So they're going to try and be as far away from each other as possible. So this is going to be ethene. All right. Okay. C double bond C, H4. Now, what is the molecular formula here? What is the molecular formula here?
It would always just be C2H because the
C2H, C2H. No, 1, 2, 3, 4.
But I mean, you know how sometimes we do the condensed version, we just get the ratio between.
Oh, you mean the empirical formula?
Yeah.
The empirical formula would be CH2. That would be the empirical formula. All right. No, but yes. The empirical formula for this group would that's very observant of you, would be CH2. Now, this is the molecular formula. I'm going to use MF for molecular formula. But watch what the condensed structural formula is. CSF, condensed structural formula. CH2. So this carbon's got H2s and CH2, and this carbon's got 2 H's. So the condensed structural formula gives us more information than the molecular formula, because it gives us a little insight into how many hydrogens are attached to each carbon. Now, when you read this, you must be well aware of the fact that those carbons are implicitly bonded to each other. We don't state it explicitly, but they are implicitly bonded together. Okay? So now, can you see that there's a double bond there? Not explicitly. So what you do find is that sometimes organic chemists will use a mix of notations. And so we'll actually physically put the double bond in there, which I think, in my personal opinion, is better. But in the NSC, they aren't necessarily going to do that. Okay, so you need to be able to go like, wait a minute. This carbon is connected to 2 hydrogens, so it's 1, 2, and connected to a carbon, that's 3. We're missing a bond. Where's the other missing bond? Well, it's between the 2 carbons. Okay. So, ladies and gentlemen, that is ethene. Right. Now, what is the next compound in the series? Please draw it for me. Propene.
So, how do they know that ethene and propene and how do they different?
What do you mean? How do they know?
I'm confused.
Yeah.
Like, for instance, let's say we're on ethene. What's the next? Instead of methane.
Okay, so if you go back here, these are the series: meth, eth, prop, but, pent. So you're going to continue. So you got ethene, then it's going to be propene, then it's going to be butene, it's going to be pentene. Are you okay with that? Sorry, Amy Kate. I do apologize. You know, it just shows you how your brain can go into a short circuit. I went into double barrel name and I landed up with a grade 11. Sorry, I apologize. Amy Kate. Yes.
Then I don't think the empirical formula would be the same in all of them.
Because of the
Because the next one has 4 hydrogens and 3 carbons.
Meth, eth, prop. Are you sure it's got 4 hydrogens? It's got 6 hydrogens.
Yeah, but how?
Okay, I know this because I know what the general formula for alkenes is, and it's CnH2n. So it's always going to be C1H2. Okay, so if you go to propene, all right, I didn't say propdiene. I said propene. I didn't say there's 2 double bonds. I said propene. So if we look at propene, if we look at propene, right? So we've got prop means 3 carbons. This means 3 carbons. So it's meth, eth, prop. We have ene, so there's a double bond there. So 1, 2, 3, 4. 1, 2, 3, 4. Doesn't matter if you put it top or bottom. And 1, 2, 3, 4. All right. Now, if you put 2 double bonds, then that becomes propdiene, but we haven't got to that yet. Okay. So looking here now, and we'll come back to we'll carry on later. All right. But can you see there, Josh? Can you see you've got 1, 2, 3, 4, 5, 6. So this becomes your molecular formula is C3H6, which means your empirical formula would be CH2.
So then in this alkaline family, we'll only ever have.
No. I'm starting off with simple alkenes. Yeah. It gets more complicated because you get dienes, trienes. Yeah. So for the time being, we're just going to do single double bonds, and then we're going to start to do 2 double bonds, 3 double bonds. We go up to 3. Okay. Now, quickly, the condensed structural formula is CH2, CH, CH3. So when you see that, where you see, wait a minute, there's a shortage of hydrogens, then we say, whoa, there's a double bond there. Because, drum roll, this compound is not saturated, it is unsaturated. Any biologists here getting excited? Any biologists? Who does biology here? You should be getting excited. Polyunsaturated fats have got double bonds in them because there isn't a maximum hydrogens potential, their maximum amount of hydrogens. Okay, so when you have purely single bonds, we call that a saturated hydrocarbon. So alkanes are saturated hydrocarbons. Alkenes are unsaturated. So can I ask you now to please do, we've got meth, we haven't got meth, we've got ethene, propene. Can you please do butene and pentene for me? You are going to encounter another problem. All right, okay, so we've done ethene, we've done propene, right? Now I want to look at butene. So if we look at butene, right, the fact that it's a double ene means that ene is telling us that there is a C double bond, C. It's telling us that there's at least one C double bond C. Okay. The but tells us that is, remember meth, you keep on saying it, meth, eth, prop, but. 4, that there are 4 carbons. Okay. Now, if we look here, we say, okay, so we've got 1, 2, 3, 4. Okay, 4 carbons. We need to put the double bond somewhere. Now, you can see that there are actually 3 places where you could put the double bond. If I put the double bond here, all right, then when I fill in the rest of the bonds using the circle test, 1, 2, 3, 4. 1, 2, 3, 4, top or bottom, doesn't matter. 1, 2, 3, 4. Okay. 1, 2, 3, 4. Right. And now we fill up with hydrogens. Now, as you have already seen, you can also put the double bond in the middle. So 1, 2, 3, 4. So now 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Doesn't matter top or bottom. 1, 2, 3, 4. Okay, so we fill up with hydrogens. Are those the same molecules? They're not. They're not. They are not. They don't have exactly the same structure. So we need to be able to differentiate between them. And so this is where we need a system in order to do so. And this is the system. We go and we say, okay, we need to describe the position of the double bond. So we need to number the carbons. So I'm going to number the carbon 1, 2, 3, 4. Okay. 1, 2, 3, 4. And the way I number it in such a way that the number that describes the double bond is going to be the lowest number. Trent, have you done this already? Okay, but have you done this section already? Okay, can you please concentrate? Okay, thank you. All right, so we could also have numbered it 1, 2, 3, 4. We could have done 1, 2, 3, 4. Now, the way we describe the position of the double bond is by looking at where the double bond is. Can you see the double bond here is between carbon 1 and carbon 2? Okay, so we use the 1. We always use the lower number. So we're going to say this is meth, eth, prop, bute. So this is going to be bute. Then I use a hyphen. 1. And because it's a double bond, the suffix is "ene." So that is bute-1-ene. If we had numbered from right to left, this would have been bute-3-ene. But we use the lowest number. So we choose our numbering in such a way that it gives us the lowest number descriptor for the position of the double bond. In the case of this one, it's going to be, doesn't matter whether we go from left to right in our numbering or from right to left. Doesn't matter because of the fact that the double bond is smack bang in the middle. Now, when you go and do chemical reactions, okay, you are going to see that depending upon where the double bond is, will have an impact on the products that are produced in certain chemical reactions, what we call addition reactions. So this is going to be bute, and it's going to be 2-ene. So when we read this, organic naming is a language. When we see that 1, we know that the double bond's between 1 and 2. Carbon 1 and carbon 2. When we see the double bond is we see 2, then the carbon is between, the double bond is between the carbons between 2 and 3. Okay. This is now if we have a single double bond. But what happens if there is more than one double bond? Okay. This is where we now add another set of prefixes. So that is butene, all right? So I want to, and I know I asked you to do pentene, but I want us to look at what would happen if we had 2 double bonds. Okay, we're going to do that now. But I just want to ask you, if the double bond wasn't there, but it was there, would it make a difference? No, because then we would just number from right to left. It would still be but1. Remember, these molecules can flip around. Okay, so let's look at this one. Let's say the following. Name. So we've got carbon, double bond carbon, double bond carbon, carbon. One, two, three, four. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Now we fill up with hydrogens. Okay, now let's name this compound. So if we look, we see, okay, how many carbons do we have? 1, 2, 3, 4. So this is going to be bute. Okay, you agree? Meth, eth, prop, bute. It's going to be an alkene, so it's going to be ENE. Okay. How many alkenes do we have? We have 2. So this is going to be diene. So di is synonymous with 2. Tri is synonymous with 3. In our syllabus, we don't go beyond 3. Okay. Butadiene. Where are the double bonds? Okay, so if we numbered from this side, 1, 2, 3, 4, it would be 3 and 4. But if we number from left to right, 1, 2, 3, 4, it's going to be 1 and 2. So we're going to number like this, 1, 2, 3, 4. And so this is going to be, now watch. This is going to be 1, I need more space, apologies. I'm going to put the bute there. We are going to need 1, 2 diene. Okay, so this means the first double bond occurs between 1 and 2, the second double bond between 2 and 3, and it's diene. Now, ladies and gentlemen, like any language, there are funnies. Like, for instance, when we've got the silent M in English, mnemonic is MN. Or pharmacy, the silent P, the people who are at IUPAC or involved with IUPAC felt that bute 1, 2 diene didn't sound as nice as buta 1, 2 diene. So as soon as you start with dienes and trienes, you need to add an A. Why? Because IUPAC says so. Buta 1, 2 diene.
Sorry, so when do you get the A again?
When it's di or triene.
Okay.
So as soon as you've got a multiple double bonds, then you have to put the A.
And also, when you search it online, it's the 1, 2 is before the compound, like 1, 2 butadiene.
Absolutely, you can do that. We don't want it in our syllabus. All right, and there's a reason for it. It's true, it's not wrong. So what Declan is referring to is you could, absolutely, and if you did this, there's nothing wrong, but you are soon going to run into issues with this when you start to put branches in, and then you have a methyl or an ethyl before it, then it ain't going to work. You'll see. When we start doing branched branch compounds, it's not going to work. That's why we want the numbers inside. But you could have here butene, 1 butene. You could have here 2 butene, right? And there's nothing wrong with that. But that's not the system we're going to teach you because of what lies ahead. You will soon enough see. Right, so this would be, you could have here, this could also be 1,2 butadiene. Okay. So if we looked at the molecular formula for this, this would be C4, 1, 2, 3, 4. How many hydrogens? 1, 2, 3, 4, 5, 6. Okay, is that correct? 1, 2, 3, 4, 5, 6. Yeah, that's 6. Okay, there's two double bonds. Okay, right. Because normally this subscript is double that, but that's only for single double bonds. All right, what would the condensed structural formula be? Okay, so it's going to be CH2, CH3. So what we do is we move from left to right, CH2, CH3. Could we do it from right to left? We could as well. We could start CH3, CH2, be the same thing. Okay. My advice is don't do it that way. My advice is go from left to right. Just works better with you. Yes.
So if you make like the pentene condensed formula, would it be CH2, CH3, CH3?
Okay, very good. We're gonna get to that. Very good question, because what we're gonna do is we're gonna abbreviate it even more. That's CH. Yeah, you'll see. You're a little bit ahead of me, but that's fine. So this is a diene. You can also get trienes. Okay. Any questions at this stage before we move on? Okay. Cool. Let's move to pent. All right. Let's move to pentene. So if we look here, draw. So I'm going to do draw pent, and I'm going to put in pent 2-ene. I'm going to choose one of them, pent 2-ene. Okay, so I'm not going to do all of them. So let's go. So I should have just done it like this to be consistent with my convention I've been using, color convention. Pent 2-ene. So pent means 5 carbons. 1, 2, 3, 4, 5. I'm purposefully doing this. You don't have to draw it all in a straight line. And you aren't always necessarily going to get your main backbone in a straight line. So looking here now, where is the double bond going to be? Well, it's going to be between 2 and 3. But now we must decide which way. Are we going to count 1, 2, 3, 4, 5 or 1, 2, 3, 4, 5? It doesn't make a difference. I'm going to count, just for the sake of being different, I'm going to go from left to right. I'm going to do it like that. 1, 2, 3, 4, 5. Okay. So where's the double bond? We put the double bond in. The double bond is going to be between carbon 2 and carbon 3. Why? Because the ene is telling us it's a double bond between 2 and 3. We always use the lowest number as a descriptor. Yes, Carl?
If you give us that drawing there where it's like that, and then you ask us to name it, and we say pent 3-ene, would be wrong.
You are going to lose some marks, yes. Because you'll see as we go on, further on, that you have to choose your numbering so that your double bonds in the backbone, you have the lowest number descriptors. Okay.
So from left to right, it will be like the top that is the dominant. Is that
Yes,
doesn't-
yeah, that's fine.
That's fine.
It's fine. So now what we do is we use the circle test. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I'm going to put it that side. It really doesn't matter. 1, 2, 3, 4. 1, 2, 3, 4. Okay, and now we're going to fill it with hydrogens. Okay, so we go all right. Hydrogens, 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 hydrogen. This one I'm going to just make it hydrogen, hydrogen, hydrogen. Okay, that is pent 2 in. Are we okay with that? Okay, now at the moment I am hopefully, I'm not doing it too quickly, and hopefully it's in a natural flow. I'm introducing super important concepts here. I want to go back here. These two are called positional isomers. Please take note. Dennis, that thing. These two are known as positional isomers. Now, the Greek word isos means equal. Remember isotopes? Okay, isotopes, elements, atoms of the same element, same atomic number, but different mass number, different number of neutrons. Isotropy means it's consistent. There's a consistency. Okay. Now, what an isomer is, and I will give the formal definitions later, are molecules that have the same molecular formula but different structures. Why is it a positional isomer? Because you get different types of isomerism or isomers, is because the reason why their structures are different is because the position of the double bond is different in the chain. So this is called a positional isomer. They've got the same amount of carbons and hydrogens, so they have the same molecular formula, but their structures are different because of the fact that the position of the double bond is different. Later on, you're going to learn about things, for instance, like functional isomers. You go to university, you start looking at symmetric isomers, cis and trans isomers. Okay, isomerism is very important. Okay, symmetry is very important in particle physics, in chemistry. Have you heard of chirality? It's got to do with symmetry. Very important. Okay. Anyway, all right. So now let's move on. All right. If we now go and we take that same, okay. I need you to all take a deep breath. Okay. It's a bit like you're playing a soccer match or a rugby match, and you're busy, you're like, yeah, okay, and you're used to the pace of the game as this, and then all of a sudden you get the ball and you go, all right? Or Carl, you're the cricketer, you're facing, and the next minute the guy puts more into his back, and it's 2 yards faster, and you're still busy deciding what shot to play, and they already have started chirping you because you missed the ball. Meantime, you didn't even see the ball. I'm about to up the pace, and in cricketing terms, give you an outswinger. You'll know what I'm talking about. Are you ready? Are you focused? Okay, here goes. I am going to change something or some things. So, I want you to name the following. Okay. Please sit firm on your seats. I'm putting a chlorine in. I am substituting one of the hydrogens with the chlorine. I am going to substitute another hydrogen with a fluorine. I am going to put another, we are going to substitute this one with wait for it. A branch. Okay. You've been facing 110 k's an hour, and now I'm just pulling in at 140. Okay. I've all of a sudden warmed up. Okay. Wait. Okay, just wait. All right. And whilst I'm at it, I think I'd like to use all the halogens. I'm going to put in an I there. Iodine. And why not? Let's just bring in a bromine as well. Let's do a bromine here. Okay, a bromine. And why not? Let's just bring in another fluorine as well. Let's bring in a fluorine. Have I got your attention? Yes, Josh.
Must we start the naming from the first carbon or from the
Okay.
compound?
Well, your double bond position determines how you number your chain. So your numbering doesn't change. Okay, now I can see the eyes are this big, and there's consternation and concern, and I can hear some wobbling of knees under the table. I can see some dissent. It's like, what are you doing, Mr. D? All right, and Mbali is saying, I think I better just go to sleep. I think it'll be easier. Okay, totally unfair to ask you to name it. But what I do want to say to you is, and I just want to check what time we end off, okay, is at 5 past, which is right now. Okay, unfortunately, we've got a shortened lessons today. So what I'm going to do is I'm going to stop here. I'm not going to give it to you for homework. But what I've done is I've given you a little trailer of what we are going to do in the next lesson. And by the end of the next lesson, you will be able to name these monster compounds. Have a wonderful day. May the force be with you.